Mic test, mic test. Awesome. So, hi everyone, no one, anyone? Been working on variational autoencoders today, building on the last episode, episode 2. And just wanted to live stream a little bit. This is gonna be live coding, so it's gonna be slow, full of errors and so on. But I will make a precise, structured episode of the contents probably tomorrow. So yeah, done pretty much with the encoders today. And yeah, here is just sampling from the latent space. As it is visible, I'm sampling the same mean and log variance multiple times. And since it is a probabilistic model, every sample results in a bit different image. And I found a research paper, I can't recall how, dated back 2016, and it detailed a smile vector, which is basically nothing else that you categorize your data set into faces with smiles and faces without smiles. In the latent space, you take the latent, calculate the mean of both, subtract it, and the difference, if you use the difference, so for example, this is an original image from the trained data set. She's smiling, but not so much. But I extracted this smile vector, and you can add the smile vector multiplied with some number to any latent vector, and then you reconstruct it, and bam. Now it's showing an error because I changed something afterwards. It's a module. Why is it a module? Something is overwriting it now. Here's a guy who is morphing into a girl and back. And we are comparing it with simple linear interpolation between the two images. So the bottom is just linear interpolation, which means you are multiplying one image with a number, and you're multiplying the other image with 1 minus that number and add them together to get a smooth pixel-wise transition. But as you can see, the variational encoder base, because we are interpolating in latent space, and then we use the decoder to get the image, we get nice structured smooth transitions. It's calling the transform. Oh, damn, yeah. I had another variable called tf. So the lesson here is, even that you are working in a notebook, the best way is to always group every code piece into a function as much as you can, because hundreds of lines away you won't remember your variable names. Where was that other tf? Yeah, torch vision as tf. Yeah, we're back. So if we just multiply it with the smile vector itself, then we get a nicer smile. Let's see. Another picture. Ah, she's pretty upset. $8.99. Can we make her happy? Not much. Not much. Even the smile vector doesn't help her. Okay, somewhat. Yeah. Face changed a little. I mean, it's smudgy as fuck, but the trained data set was only 5,000 images. It's only a variational encoder and only 1,700 test images for 100 or 200 epochs. Pretty small model, but it's not so bad. Here I used an image of myself. As you can see, I don't look like myself. But at least not me is smiling. So one more thing I wanted to do with this. Is to actually create a GIF from this. So let's use a code piece that already makes a GIF. Let's take her just like this. EMG no smile. That's the reconstructed smile, okay. We don't need the LARP code. Yeah, so here is alpha and beta. Basically, alpha is an array that steps up from 0 to 1 in 25 steps. Beta steps back. This basically transposes these row vectors. So then concat, and then we can use it to interpolate between ZA and ZB, which in this case, yeah, well, ZA is just Z, and this is Z plus the smile vector. These will be the frames. So we don't need this anymore. Definitely don't need this anymore. So reconstruct the image with no smile. Get the latent. Get these interpolation factors. Concat them into a single one. Interpolate to get all the 50 latent vectors that we need. Now we decode, and I think the decoder only returns the reconstructed values, and without showing anything, let's just print the shape. That's just one because we actually need, let's call it Z interp. So that's 50, okay. Yeah, the head also changes a bit. But I mean, back in 2016, this was a nice finding that you can make people smile on an image with just such a simple calculation in the latent space. Just subtract one mean from the other and you have the smile vector. Let's scale it up a little bit. Okay. I would want to save this. GIF show, GIF save the same way. New function, hopefully it works. And pretty soon this is getting so big that I will have to move it to a real project. I'm into Python files and structure it normally, not in notebooks. Mm-hmm. No such folder. Okay, pretty cool. And in the last episode we worked on this one, but I already modified it. I upload all notebooks to the school community. It's free to join if you want. All videos, the notebooks, me, help. If you have questions and I can answer, I'm happy to help. This was in the last episode. And I just added a visualization for the latent space distribution. But it's for the VAE, this one. As you can see, it's just a blob. But since we train the variational encoder using the normal distribution and the KL divergence loss forces it to be kind of around the center, the mean, and the STD to be 1, meaning most, if not all, the values are, well, at least 99% of the values are between -3 and 3, and of course there's a bit more around here. So if we just rerun this for the current model, yeah, it's the same. It's for, it gets the latents from the test. And what if from the training data set? Yeah, so it's pretty much, I mean, we could further tune it, change it based on how we treat the KL divergence. So probably we could try the original that I wrote. Binary cross entropy, which I tried first, just yielded smudges, and that's already an exaggeration or a compliment because it was just a big blur. Mean square error is much better for these images. But we can't train only with MSE because then it will basically become just a normal autoencoder, since it won't force the network to learn around the standard normal distribution. Import bias NP. So this is the KL divergence term. And SE is what I do here, is that I gradually add the KL term in. So in the first few epochs up until 50, I basically mostly only use the MSE and then add the KL term, which kind of pulls it back in. And so phi goes from 0.5 to 1, and it's increasing as the sinus increases up till epoch 50 to the top of the sinus, and then it stays there. And the total loss will be the mean of these two terms. I like to memorize this reconstruction to be able to compare. No, I'm not switching language, I want to take a screenshot. So this is going to be without smooth KL introduction. And if we retrain it, I mean, I trained it for 200 epochs just to see how much better it gets. The training loss at 100 was 26k, it's just 24k here. Eval loss 29 versus 2826. We're not doing anything production quality, so just to save time, 100. We will see in 100. Could mix up stuff. because there is no full KL up until epoch 50, but let's try and see. The EVA model doesn't work because... Oh, right. Wow. So where is pi? If numpy doesn't have pi, what does have pi? Math? Math doesn't have pi. Okay then. There's pi. So the loss here will actually increase as we get to epoch 50 and introduce the KL term. And the downside of developing AI models is that you have to wait a lot while they train. So when doing the first evaluation, the epoch is set to 1000. So the initial loss here, 125, takes into full consideration this KL term. Not sure if I should null it out, or because then at epoch 10 you can see that there's almost no KL term. And it looks weird. The learning rate I just kept fixed for now, although the scheduler is still here. But the initial learning rate is this, and the final learning rate is the same, so this will in practice not do anything. While I wait, I could either do research on diffusion models or find a new research paper for autoregressional diffusion models. There are a few now. Or go with VAE. Okay, so by now, if I didn't mess up anything, the KL term should be introduced. I mean epoch /50, but my minimum 1. So it will pick the minimum. So this can get bigger than 1, and minimally it's 0, take half pi. But the loss didn't grow. Am I even passing the epoch? Yes. It would have been better if I just log how much KL term I had. So I'm guessing I'm going to do that. But not here, here. So that's going to be the actual scaled KL. Let's see. Oh, it changed a lot. It changed a lot. Jeez. So, oh, where did it go? Why? So this one, why are you jumping around? So the right is using the KL term from the beginning, and the left one basically gradually turns it on after epoch 50 it's fully on, but up till epoch 50 it's not. I don't know. It's strange. It's just weird. It's much worse. Let's just disable this. Phi would become 1.0. Rerun training. Meanwhile, I do use ChatGPT for help, but for learning. There is no generated code in here. I do use generated code, for example, this stuff I didn't want to deal with, extracting the smiles from the images. I had to create this. These are the indices of those images from the training set where the person is smiling. Obviously, that's not my focus to extract such things, so GPT could do this. I'm happy for it. It saved me time, but it doesn't help me understand what I'm doing, and my primary goal is to understand it down to the bottom, every piece of information. So you can find basically this faces 128 dataset on Hugging Face, because there was a faces dataset with large images, 1000 by 1000 images, and I didn't want to use that for training. For toying around 128 is more than enough. And I try to resize those images here with t.resize. But actually what happens here is that it only runs this transformation when you pull from the data loader, meaning during training you don't only wait for the CUDA kernels to complete, you wait also for, probably with CUDA kernels, also that the image resizing takes place. So it was just horribly slow. So basically you can forget the resizing unless you know a way to trigger them on load. So it's just much better if you have a data set that you find on Hugging Face and it's not so compatible. You need to resize it, then pull it, resize it with a script and re-upload. Now there's this har cascade file, har cascade smile. That means there are probably other har cascade XML files for all kinds of emotions. It would be interesting to toy around with those, but not today. After trying this and either disabling the smooth mixing of the KL term or keeping it, I will just continue. So the KL is 6, 5. And some formatting would be nice. So it wasn't a KL term, it's something else. It's that it's probably because the other function used, it didn't take a mean, it just added those two together. Training mistakes are costly, very costly. Yes, because the loss, this K out, and the loss is a scalar, but the KL isn't. So let's print the shape of the KL. '64. Use the mean or use the sum? Use the sum. So we have mu and log var, which are latent dim sized vectors basically, and but for each batch, so it should be batch latent, and we sum on dimension 1 on latent all these together, and we end up, as we saw, with only the batch. So we could just here sum again dimension 0. So we arrive with a number that is the KL term for the entire batch. Meanwhile, I should pull up the research paper on my screen about the VQ variational encoders. (2017). But I'm not really interested in VQ VAE itself. I'm interested in Gini 1. Is it really Gini 1? Was it released in 2024? I mean, it looks like it. Submitted on, just gonna move it here instead. Submitted on 23rd of February 2024. Gini generative. It makes sense. So it's actually an acronym. Generative interactive environments. It's trained in an unsupervised manner from unlabeled internet videos. So what we will need for this is basically just download some proper YouTube videos, or I'm gonna check Hugging Face for some data sets. Video. But actually the goal for learning, I was thinking about maybe making a GIF that you can control, a small, like 200 by 200 GIF. So instead of internet videos, I might look for thousands of video game sprites and normalize the data into a proper format for learning. And what's magical is that you can actually control this model because it learns what action could have triggered that next state based on only the frames. So it learns the actions in an unsupervised manner, and you fixate that those actions, you just put like, I think they put 8 neurons there, but for the cursors or WASD control, we would need only 4 in the action model. So, and you actually just fire those neurons whenever a key is pressed for the next frame. But of course, in this Gini model, the original one, you can they wired up an LLM, so you can use text. But all right, let's open up the research paper, because I just recalled that yes, you can use an LLM, but an LLM is not directly connected to Gini. You just use an LLM to generate an initial image, the first frame, and you feed that into Gini. So you can use any LLM as long as you end up with a picture like this. So this is the first frame, and if it has enough knowledge and it was trained enough, then it will generate the next frame. And also it will figure out what action triggered that next frame. So implementing the model itself won't be that easy. It probably won't be that hard either, but the dataset itself, to find such a dataset and then be able to train it on, well, I have 2 GPUs, RTX 5070 60 gigabyte. So in Pytorch, I will have to train it with FSDP, or maybe with deep speed if it's so big, because I guess it is going to be big. And then with there is an optimization in deep speed where you can put the whatever part of the model doesn't fit, or the data doesn't fit into VRAM, it just puts into normal RAM or even your SSD. So that way you can train huge models, but it takes a very, very long time. So reviewing this paper, the fun starts around here somewhere. They start with the latent action model and describe that, but the ST transformer is also very interesting. Here is the video tokenizer. That's where you feed the frames into, and also the latent action model. But as a first implementation, it would be just nice if you fed an image into it and it could just generate the next frame, so like for a while. And I believe this does it in an auto-regressional way, unlike diffusion models where, for example, you go on Midjourney or Kling, and all the videos are like 5 seconds or 10 seconds, so they have a fixed size. This doesn't. This works like ChatGPT. It takes n previous frames. I think Gini takes all the previous frames up until what it generated, and it outputs the next frame. and at the next step it also takes that frame, and so it can keep continue generating frames for a long while. It's another question that I mean, it's another thing that after a while it might become unstable and generate trash, but there are also possible ways to stabilize that. I mean, Genie 3 can generate very, very high quality stuff for like 5 minutes or 20 minutes, I'm not sure. But yeah, so the video tokenizer, and why I'm messing around with VAEs, it's not because they are so interesting in themselves. I mean, they are, but they are pretty old, so the next step is to implement VQ VAE with an ST transformer. And an ST transformer, the original research paper is really hard to read. Let me show that. So it's basically, is it this one? I don't think it is. No, this is a different one. It builds on the, it's actually called spatial temporal transformer. And yeah, got the paper. I think this is the original one. And I think it was for traffic control, traffic flow forecasting actually. So it's a lot with lots of complex diagrams, and I mean, it's on one hand it's good that it's detailed. On the other hand, lots of stuff is just analysis and existing already known architectured, written up in complex math forms. We introduced the scale dot product function to consider bidirectional temporal dependencies. The Pytorch implementation is much easier. Of course, you need to know the background math. But this paper is just pages and pages, math after math, and I enjoy this kind of stuff to a degree, but if I can find another source that details this in a more digestible format, then that will be my choice. So far, what I gather, the ST transformer is like, well, the temporal transformer. I'm not sure the original transformer that ChatGPT uses. It has this triangular mask. But this is basically, it should be just two transformers on different data, because we're dealing with images here concatenated. So the video tokenizer, as a first step, compresses videos into discrete tokens to reduce dimensionality. That's what we are doing with the VEAs. VAEs, but we need to compress them into discrete tokens, and that's the reason we will need the vector quantizer. Typo. Takes in T frames of video. And the channel is the last axis. The input generating discrete representations for each frame. These are our latent vectors, where D is the size of the discrete, that's latent dim. Tokenizer is trained using a standard VAE objective over the entire video sequence. So the objective is VQ variational encoder like, but they don't really say where is Gupta et al. Mask with mask visual present training. What? Mask visual pre-training for video prediction. And who were the other two? Villegas and Jan Letsun. Sorry if I misspelled it. Variable length video generation from open domain textual descriptions. 2022. Jan at. Yeah, Jan. It's Yang. 2023. Oh, that's a different Jan. That's 2023. That's good. Temporally consistent transformers for video generation. Nice. I hope I don't need to do again as well. It doesn't mention in the Gini paper, and they just say they are following prior work. Figure 6. Yeah, that's not really detailed, is it? It has an ST transformer. Which let's assume we can do, because it definitely doesn't have a hidden GAN inside its code. But if it's like mask width, obviously Google and DeepMind don't want to be too detailed about their findings. It's like they say as much as you need to be able to release a research paper and brag about what you did, but I think they didn't even bother to do the same with Gini 3. Yeah, that's 2021, that's not the same Gini. Hey, at least we have something to go about or go on. Mask width, as we use mask kit. We use, damn, come on. We use mask git and an ST transformer. We seek a more agentic goal and explicitly learn a latent action space from data, allowing users or agents to play the model using latent action condition predictions. This is like really a Demis Hassabis way after co-learning. Okay, let's see mask git. Mask generative image transformer. I mean, we are already generating images with the autoencoder, so this could be the next video. Strictly on small images though. Yeah, so this is kind of an in-painting model. That's how they use a sequence, an autoregressive transformer. So you start decoding the pixel values on the top left corner, and you go row by row, line by line, cell by cell to arrive at that image with autoregressive transformers and scheduled parallel decoding with mask git. Yeah, so here is the visual tokens, the code book actually. So it works with a discrete set of latent vectors, basically a grid of latent vectors. What I'm interested in is how this encoder and decoder look like in fact. Mask Git follows a two-stage design. Tokenizer that tokenizes images into visual tokens. I mean, yeah, you have the decoder there, you get the latent codebook, decode it back to the image just because for training, and the bidirectional transformer model that performs MVTM, mask visual token modeling, i.e. learns to predict visual tokens masked at random. So basically you have that code book, as I understand, you apply a mask on it, and then you learn to reconstruct the full code book. All right, let's go back to where were we? We were here. Same, haha. Something is not right with the KL term for sure. What's the default reduction here? Default is mean. And so sum basically let's give a shape like 3, 5, 6. Let this be monkey. Print monkey and print some monkey. So it sums up all elements, which is what we need exactly here instead of performing two sums. So that's one simplification. And this negates the whole thing. Because the KR term is, I think, positive if the two probability distributions are far away, and it becomes 0 when they are the same. And we need the exact. The loss is positive, so that's gonna be negative if they are not the same. So working from the math formula, it's minus half sum one plus log var minus mu squared minus x per log var. So this is definitely the proper formula. And then the total loss is mean squared error plus KL. I'm just not going to mess with this phi for now. So to put it in another way, the KR term penalizes if a probability distribution is further away from another one. For now, this was the first live. I'm gonna do some VAE research and implementation and record a video tomorrow, and probably come back with a live implementation of the VAE. So bye.